Second day of the verified software tools and experiments workshop. My name is Kim Larsen from Aalborg University in Denmark, and I'm one of the organizers of this workshop. And I have the pleasure of chairing these two sessions of this afternoon. At least in Europe, it's afternoon. So we have 6 talks ahead of us. So I should say, as it says in front of me now, that the meeting is being recorded. So if you don't want to be part of this recording, you can mute your mic, or maybe even better, close down the camera. But I think it will start recording now. So the first speaker of today is Naijun Zhan, who's a research professor from State Key University, State Key Laboratory of Computer Science, Institute of Software in the Chinese Academy of Science in Beijing. Naijun got his PhD in computer science also from ISCAS in Beijing, and an MSc in computer science and BSc in mathematical logic, both from Naijun University in '96 and '93 respectively. And prior to that, Naijun was at the Institute of, worked at the Faculty of Mathematics and Informatics in the University of Mannheim in Germany from 2001 to 2014. And he is now a distinguished research professor at the Chinese Academy of Science and winner of the Outstanding Youth Fund of National Science Foundation of China from 15 and respectively 2016. And I'm sure, as many of you know, the research of Naijun covers a good deal of formal design of real-time embedded and hybrid systems program verification, and so on. This is what he wrote in his bio, with numerous papers and I would say books and book chapters. So I'm very much looking forward to the presentation of Naijun. So over to you.
Hey Kim, thanks a lot for your kind introduction. So it's so nice to meet our friends here. Particularly, I thank the organizer for inviting me to be here. Today I will present our recent work on extending hologic to hybrid system, which joint work with Bofar Zhan and Suning Wang, both from our institute, and Dimit Gan from Bulgaria Academy of Sciences. This is the outline of my talk. Firstly, I will explain the motivation. Actually, as you knew, that several physical systems are widely applied in our daily life. Particularly, many of these systems are so-called safety critical. It means that any fault will result in catastrophic result. For example, when the train crash accident in 2011, and the Japanese Space Center telescope asteroid was lost just after launching 1 month in 2016, and so on. This is the formal definition about the several physical system and some features I assume all of you are, knew it. So actually, you see that several physical system can be modeled as the hybrid system as given in these pictures. So the crucial question here is that how can we design several physical systems so that people can bet their life on, as pointed out by Jonathan Wen. So currently there are 2 paradigms on the design of several physical systems. One is informal. It's called a simulation-based design, advocated by industry, which is very intuitive, easy to be used by engineer. Is also efficient, but it is incomplete, means that it's difficult to guarantee the reliability of safety critical systems. The other one is called formal design, advocated by academia, based on formal methods. So advantage of this method is reliable. Can be used to guarantee the reliability of safety critical system. But the problem is that it's very costly. Also, it's not easy to be understood by engineers. So For the formal design, there are two major techniques for the verification of a stable physical system. One is the model checking. In model checking, hybrid systems are modeled as hybrid automata, and verification is conducted by computing reachable sites. Its advantages is that models are very intuitive. Verification can be done automatically. Once you disprove the property, you can get the control example. The disadvantage of this approach is that it lacks of compositionality, means that it's difficult to model complicated systems. Also, because of the high complexity and undecidability of several physical systems, normally model checking, the scalability of model checking technique is very poor. Normally, it can only be applied to do the bounded time verification. So, for model checking, how to compute reachable site is challenging. Many techniques based on abstraction, approximation, numeric computation, and so on have been proposed. In contrast, for sample in hybrid systems are modeled as process algebra like formalism, like a differential program, hybrid CSP, and so on. Verification is conducted by sampling based on underlined specification logic together with invariant generation. Its advantage is that it is a compositional. Normally, its scalability is much better than model checking technique. It can do the unbounded verification. The disadvantage of this technique is that normally the specification logic is are normally complicated only with weak relative completeness. Also, the verification is normally given by active interaction, not automatic, at most semi-automatic. So the verification efficiency is very low. Even you can detect bugs, but normally you cannot get the control example as with model checking. Also in sample in technique, how to synthesize more expressive invariants is challenging. Actually, there are many work have been done on deductive verification of a hybrid system, particularly differential dynamic logic due to Andre, which is an extension of dynamic logic to hybrid systems. In differential dynamic logic, hybrid systems are modeled with differential programs. Andre proved its continuous relative completeness and discrete relative completeness. It also developed several variants for different computation phenomena, like for stochastic differential equations, AI system, and so on. Andre and his team also developed some tools like Kayamara and Kayamara X, and so on. So the problem with differential dynamic logic is that it cannot cope with concurrency and communication in an explicit and computational way. Also, there are many other approaches like hybrid even B extended duration calculus. But with this approach, the disadvantage with this approach is that it cannot provide very powerful proof composite. So a powerful specification logic for hybrid systems that can deal with concurrency and communication in a composition way is desirable. Now I will give a brief review of Hoare logic. Hoare logic is due to Floyd and Hoare, which is the cornerstone of program verification. Actually, there are lots of important extensions to Hoare logic. Here I just mention of some of them, like to the concurrent programs, to mutable data structures, to real-time and hybrid system. I will focus on the extension to hybrid systems later. Also other important extensions like to security, to quantum Hoare logic, and so on. If you are interested in the history of Hoare logic, maybe you can have a look at the paper read by Abt and Odrog 2019 on the history, 50 years of history of Hoare logic. Now I go to the technical part, how our work in the past decade on extending Hoare logic to hybrid system. We built two versions. One is based on duration calculus. The other one is just based on first order theory of differential equations. Now I will give a brief introduction to hybrid CSP. Hybrid CSP is an extension of CSP due to Professor Ji-Fen He by introducing continuous evolution to model continuous evolution and timeout interrupter and communication interrupter to model the interruption between the continuous evolution and discrete jumps. This is the syntax of duration calculus. Duration calculus is an extension of interval topology due to Zhou, Hoare, and Yuan. The first line is the definition of the state expression. The second, which is interpreted over the time domain. The second line is the definition of the terms, which is interpreted as the real over intervals. The third line is the definition for the duration formulas. I think the first two is atomic formulas. The third one is logical implication. The fourth one is the logic chop. This is the Canonical star and the fixed point, least fixed point, and extension quantification. Duration formulas are interpreted as the Boolean function over intervals. So for the DC-based hybrid Hoare logic, we interpret each HCSP process with a duration calculus formulas. We call it duration dilution semantics. A DC-based Hoare tuple looks like here. A, P, G, A, and G both are DC formulas. We see this Hoare tuple is valid if only is if and the corresponding DC formula A chop 2 implies ligation the DC semantics of P conjunction ligation P chop P is valid. Okay. So we give a proof system for valid Hoare tuples, including a set of axioms for primitive construct like here with the precondition 2 and the process P and the postcondition semantics of P. Here the semantics of P is given by the DC formulas. Because of I don't think I have enough time to explain the details. If you are interested in this part, maybe you can look into our paper. Also, we give a set of rules for compound constructs. It is just simply decompose the Hoare tuples for the compound construct to the corresponding Hoare tuples for the subterms. For example, for the sequential composition, we just use the chop operator. For internal choice, we use the conjunction and disjunction as usual. For the loop, we use the Canonical star, and for the parallel composition, we use the conjunction either. But we need to compare which process P or Q is finished earlier. So for this system, we prove its completeness related to the duration calculus. So the technical details can be found in this paper. Now I will introduce I will introduce our recent work on simplified hybrid Hall logic. It's purely based on the first order series of differential equations. Here, in order to deal with communication and timing constants, we introduce the trees. But here, trees we consists of two types of blocks. One is called the continuous blocks, which is used to model some the continuous evolution. The other type is called the communication blocks. That could be output event, input event, or communication event. Certainly, we can put the two synchronize two traces via common channels. Like here, we denote as the TR1 synchronized with TR2 with the common channel CS to result in a new trace TR here. We just have a look one example for this process. With one sequence follows CH send out value 3. We have a possible trace TR1 here, but be careful here. X map to 0 means that in this duration 1, X keeps constant to 1 here. So empty means that during this evolution, low input, low communication event is ready. So afterwards, you see that the output events happened.
So Naijun, you have like 5 minutes left, a little less.
Okay. I think I can finish it. Thank you.
If you want some good questions and you want.
Okay, sure. Okay, so here is the possible twist for send out the value 3. You see that this means that for this output action, we need to wait for 1 time unit. During this waiting, you see that the output is ready, and also we keep the X to 0. So afterwards, so this output event happened. Similarly, we can have a possible trace for this input action. So be careful. You see that we can put synchronize TR1 and TR3 together to get this new traces, but we cannot synchronize the TR2 and TR3 because the communication event are not compatible, because you see that the output and the input both are available for 1 time unit. Okay. Mm-hmm. So here we define small step semantics for HSSP as usual. So I will skip the details. We also define a big step semantics for HSSP, means that, for example, CS to SPTR means that C carries initial state S to the final state S prime with resulting trace TR. As expected, we can prove the equivalence of the two semantics. So here is the details for the big step semantics. So based on the new operation semantics for HSSP, we can define the Hall triples like here P, C, Q. P and Q are assertions on state and traces. C is HSSP processes. So it means that starting from initial state and the trace satisfy P, after executing C, the final state and the trace satisfy Q. So we define the inference proof system for the new inference and valid Hall triples with respect to the new semantics. The rules for assignment, sequence, conditional, internal choice, and repetition as usual. For repetition rule, we define the invariant. So for the parallel rule, we need to reason about the synchronization of traces. So the whole proof system consists of 4 parts: axiom and inference rules for first-order survey of differential equations, axioms and inference rules for timed traces and readiness, and the axioms and inference rules for HSSP constructs, and some general rules like Hoare logic. We just show that the one example for the trace and readiness for the first inference rule means that for the communication, the 2 parties both are ready. You see that then we can get we put these 2 traces together, we can get a new trace with a communication. Okay. For the axioms and inference rules for HSSP construct, we just list some of them here. For output, you see that we consider 3 cases: the communication, the event happened immediately, and the communication event happened in the finite time, and the level happened. It means you have the event wait for infinite time. Similar for input. For the continuous evolution, we consider 2 cases. Means that the evaluation level happened because the bound condition becomes false at the beginning. Then you see that the second case means that once in the finite time, the continuous evolution terminates. So we should guarantee the corresponding version of the post condition satisfied, so that we get the rule. For the parallel rule, we simply use the conjunction to specify that, but with the trace synchronization. I will skip the technical details. So we can prove the 2 relative companies, like the Andre's work for the differential dynamic logic. We can prove its continuous related companies and its discrete related companies of this proof system. Kim, how many minutes I have? This is the 2 support. So we have proof a system for the 2 versions of hybrid Hoare logic in Isabelle, integrated with other tools. The overall architecture of the 2 chain looks like here. I think maybe I need to skip this case studies. I will go to the concluding part. So for the future work at the logical level, we need to consider how to extend the logic to more complicated property like uncertainty, particularly AI components. Possibly we can borrow some idea from Andre's work like a stochastic differential dynamic logic and differential game logic. Also for the fault tolerance, security and privacy and other issues. We also need to consider the invariant generation, particularly for some complicated behavior like time delay, stochastic dynamic behavior. And we also need to focus on how to improve scalability and efficiency of the existing invariant generation technique. Certainly, you see that currently template-based invariant generation are very popular, but the challenging problem is how to predefine templates and so on. At the implementation level, we need to consider to define a simplified assertion language to ease reasoning, also differential invariant and other rules for reasoning about ODE and improving automation. Also, we need to consider more case studies. Okay, thank you.
Thank you very much, Naijun. And thank you for speeding up here at the end. So because that leaves us for some time for some questions. If you want to, you can raise your hand on virtually or in real. I'll try to capture it. There was a hand there. Who was that? Maybe I saw one hand. It's really difficult. Andre, sorry, yeah.
Yeah, thanks, Naijun, for the interesting talk. I was wondering something I never really fully understood is, are you going for an interleaving semantics of the parallel processing? Because that's what the examples and so on always end up looking like at the end. And when you look at these semantics, is that what we have to keep in mind? Or I realize you didn't have time to talk about it in detail, obviously. But is that the right spirit to have?
You mean here?
Yes. Are you going for an interleaving semantics for the parallel? Parallel combination?
Okay. For the bigger step semantics. Let's see. Actually, we have set off rules, but here we just put one here. I think, yeah, just have one rule here. Yeah, you mean this rule?
Okay, maybe I don't understand this notation that well.
But I think the way you combine traces is interleaving, where you synchronize some common actions, right?
Right. Yeah.
Okay. Thanks.
I'm looking at the list here. So this, you claim compositionality now. So what was the proof rule for parallel composition again?
You mean that for the DC-based proof rule or the simplified proof rule?
Whichever you choose. I mean, yeah. So I would like to say,
okay.
How can you infer properties of a parallel composition?
Yeah, for the DC-based, you see that it's easy. You see that you just use the conjunction. For the parallel rule, you see that once we have you see that the two Hoare triples here, we can put the precondition together, but definitely because you see that possibly the starting time is different, so we put we appendix some sub-intervals here so that we share the same length of the intervals. For the post condition, you see that the first case maybe you see that P is finished first, so we need certainly we need to append more time to the P. So means that Q is has been satisfied, but because P has finished, so we keep the all variables in P constant. Afterwards, so this totally is a conjunction with H. So the vice versa, you see that we assume that Q is finished first, so we need to append some more time to the Q because Q need to wait for.
But I have a question. Naijun, I have a question here. So, but can't P and Q interact with each other through shared variable in that time? So, in fact, you fooled me a little bit by calling it AG. So, I thought these were like assumed guarantees. I mean, I assume under the assumption that the other guy will not manipulate the shared variable more than that. Then I guarantee something. But so I don't understand how this can be, in some sense, even a sound rule. Because what if P and Q during their execution?
Oh, yeah, you're right. Yeah, Tim, here we assume that P and Q cannot share the common variables. Okay. Yeah.
Okay, good. Yeah. Okay, then I'm happy.
Okay. Because you see that we use the communication. So here we assume that P and Q cannot share the local. Yeah.
Thank you. Yeah, I don't see any more questions.
Kim Sanjeeva here. I had a follow-up to the question you asked.
Yeah, yeah, sure. Go ahead. Go ahead.
In a cyber physical system, there also is communication through the physical variables. You know, you can't somehow just stop flying if you're a drone. You'll just drop out of the sky. And so apart from all the synchronization, you also need to make the physics or the passing of time all very smooth. So how do you deal with this sort of implicit communication that's happening through physical quantities. Thanks.
Oh, actually, you see that currently in HCSP for this infinite communication, we cannot model such implicit communication. You have to use some explicit. Actually, we consider the translation from the semi-link state flow to HCSP. For this physical part, we need to introduce some explicit communication channels to model.
I think thank you very much. I think in the interest of time, I think I want to cut it short here. There is a nice chat, so you can continue interacting and even post full papers or proofs to set it up.
Okay, sure.
So thank you again, Naijun, for your nice presentation, and I want now to continue with the